Hi guys, welcome back. I think you can hear me loud and clear. Uh, in this session, we're continuing the PS Bhimbra electrical machines questions. We have already done 11 parts. Right now, we're at the 12th part. You can check the link in the description for the all different videos of this playlist. Okay, there is a full playlist for PS Bhimbra electrical machines questions. You just follow that. Now, in this session, the questions, why I'm saying PS Bhimbra is the questions what you're going to see now, they are really amazing questions. Okay, with the help of these questions, you'll be able to recall all the concepts what you have learned and all the concepts what are there actually in DC machines, you'll be able to recall with the help of these questions. So I recommend all of you to solve these questions. If you see, I'll just take you to some of the questions. Yeah, look at these questions. How nicely, how creatively, how beautifully questions are framed. Okay. So if you answer these kind of questions, look at this. It's asked for some accidental interruptions, uh, about the starters. Different concepts are given here, not just question answer sessions. So that's the reason why in case of electrical machines, PS Bhimbra is very important. In case of power systems, CL Wadhwa is very important. Okay. CL Wadhwa backside equations. In case of Part-12 is also PS Bhimbra backside equations are there. We'll also see that. If you want to see power systems backside equations, we already have a full online test series on these power systems with a detailed solution. It is there in our website or app. You can download the app and you can check this. Yeah, power systems CL Wadhwa with a detailed solution. We'll get all the questions here. Okay. Anyways, let's begin with today's session where we'll be talking about power systems. Sorry, electrical machines, DC machines. Okay. To start with the first question, shall we begin? Just give it in the chat. Are you guys ready? And I want you to respond quickly also to the questions what I'm showing here. Yeah. Let's begin. Try to answer this. Here's the first question. Look at the question, try to read the question and try to answer this question. Give your option in the comment. Don't take much time. You read the question? You got the answer? Give it in the chat. Okay, let me explain here. Consider the following statements. At starting, careful here, the concept in your laboratories when you are doing experiments, you do keep these kind of settings. It is said at the starting, field excitation of DC shunt motor is kept at maximum value. When you are doing experiments on DC shunt motor, I don't know whether you noticed or not, there is always a resistance in series with the armature and there is a resistance in series with the field winding. There are two resistances. Okay. So when you're starting a DC shunt motor, your instruction manual says always keep the armature resistance, armature rheostat at maximum position. The rheostat should be at a maximum position and field rheostat is at a minimum position. Always they'll ensure you to start your DC shunt motor with this setting. This should be at a minimum position. Okay. Why? Because why it is said to be at minimum position? Why you should ensure field resistance at the beginning of the DC shunt motor should be at the minimum resistance. Minimum resistance means maximum current. Maximum current. Current is maximum in the field winding. Why current is maximum? When current is maximum, flux is maximum. Flux is maximum. You should ensure the flux is maximum and armature current is minimum. Because at the starting, you don't have back EMF opposition. So by keeping this resistance at maximum, you're reducing the armature current further down. Okay. just to handle the back EMF at the beginning only. Now when it comes to this, why it should be kept at minimum position or maximum flux you should allow? Why? That's the question. Why maximum value of DC shunt motor field excitation? Field excitation is maximum, means why flux is maximum, means why resistance or rheostat is at minimum. See, one line of question has brought a lot of concepts. You have to recall the concept. That's the beauty of these PS Bhimbra questions. That's why I ask you, every one of you, if you study the concepts, if you understand the concepts, for you to practice or revise the concepts, PS Bhimbra backside questions are the best. Okay? In the same way for power systems. Alright? Yeah, why? Sparking, to reduce what? To reduce sparking at the brushes. Yes. Yes, it will reduce the sparking at the brushes, because when flux is maximum, armature reaction effect will be less, because phi A is armature reaction, phi SH is shunt field winding. When shunt field winding flux is high, obviously compared to, I'm just giving some random numbers, compared to 100, 2 is very small. You can ignore that 2, means you can ignore that armature reaction effect. Okay, when this is high, a slight variation in armature flux doesn't really matter. Okay, so sparking at the brush is reduced significantly when you keep it at maximum. That's absolutely true. And acceleration time reduces. Acceleration time means to reach its maximum speed, it won't take much time. In small time itself, it will quickly reach to its maximum speed, because it has high flux, more torque is there. When there is a more torque, because the high flux, because torque is proportional to flux, and it will quickly rise to its maximum speed. Yes, it will reduce acceleration time. Okay, and then starting current, will it really reduce the starting current? Means statement 1, 2 are absolutely right. So with that I can say this is wrong answer, this is wrong answer. You'll have to figure it out between option A and option D. Now for that you'll have to either check 3 and 4, any one of these two. If you check, you will get the final answer. Starting current, do you think it will really reduce the starting current? Yes, give it in the chat. Do you think it will really reduce the starting current? Yes, definitely reduce the starting current. Why? Why? Because back EMF, we know back EMF is proportional to flux. Back EMF is proportional to flux, and of course it is proportional to N as well, speed as well. So higher the flux, higher the back EMF, lower the starting current, lower the current. Okay, be it starting or running current. So yes, it will help in reducing the starting current also. So after checking these 3 statements are correct, I can directly say this is wrong, this is right answer. This is right answer. Now let's verify the 4th one also. 4th one, what is this? It will reduce the voltage dip. See, the moment we know at the beginning it will draw, any motor draws a high amount of currents. Starting currents are very high. When starting currents are high, voltage drops are very high. That's why when you turn on AC or when you turn on any motor, for the matters, maybe your water pump motor, when you turn on, there will be slight fluctuations. There is a slight flicker in the light bulbs. Why that slight flicker? Because at the starting it will draw high currents. When it is drawing high currents from your main source, there will be voltage drop in the different junctions. So that voltage drop, voltage dip will be reduced because starting current itself is reduced slightly. Yes, that will have a good effect on voltage dip as well. So this is also correct. Option D is correct. I hope you got to understand a lot of concepts with the help of this beautiful simple question of PS Bhimbra. Okay, we are at the 12th part. All 11 parts are done in the previous lectures. We just check the link in the description, okay, for the complete playlist. And you're gonna love this electrical machines and PS Bhimbra as well. Okay, and we have this amazing course also. If you want to go for a course, we have this 0 to hero course on electrical machines, DC machines especially. For that, just visit our website or download the app. You can watch some of the free videos also, which are available with the beautiful animations. The DC machines animated videos are there. You can check that. With that, you'll get better concepts. You'll understand the concepts much better. All right. Let's go to the next question. Yeah. Try this now. Try this now. See how beautifully the question is asked. Simple concept, simple question, but I think you'll get some maybe roadblock in answering this. Let's see. Try it first. Try it first. I think you tried. Okay, let me give the answer. In the field current of a DC shunt motor, okay, we're talking about DC shunt motor. First, freeze that. Whenever you see the questions, it is talking about a DC shunt motor. Keep all your concepts and mind tuned to this DC shunt motor. Now it is talking about field circuit of a DC shunt motor equipped with a 3-point starter gets interrupted accidentally. Means a field circuit is interrupted accidentally when it is connected through a 3-point starter. Okay, we have a beautiful animated video on YouTube itself. You just check that animated video. Nice animation is done by a team. So there you'll understand what's the beauty of 3-point starter. Okay, just search it, or we'll add the link in the description for the 3-point starter. You're gonna love that video as well. I think it's in Hindi, I think. Okay, check it out. But animations are really amazing for that. So it said when there is a 3-point starter and DC shunt motor is this, and the field circuit is accidentally interrupted. We know in case of a 3-point starter, field circuit is connected to no volt coil. The moment a field is de-energized, the moment a field is demagnetized, no volt coil also get demagnetized. Once no volt coil is demagnetized, the handle will be released back. The handle will be released back. So armature winding will draw high currents. No, starter arm will fly back to off position. Absolutely right. Absolutely right. Means that starter handle will come back because of no volt coil. It will consider it as, it will take it as there is no voltage because field is de-energized. Okay, that's what the drawback, even when that's what the drawback to go for 4-point starter. This is one of the popular interview questions also. 4-point starter, 2-point starter is for DC series motor, 3-point starter is for DC shunt motor. Now people think 4-point starter is for DC compound motor. Okay, it's not true. For DC shunt motor even, we'll use 4-point starter because there is a slight disadvantage with the 3-point starter. What's the disadvantage? Of course, it's not accidental. You know, it's not a disadvantage. It may be accidental, it may happen. But the disadvantage is when you're trying to control the speed of a DC shunt motor using a field excitation, means you want to go the speeds above rated speeds. To go to the above rated speeds, you have to reduce the flux. That's the only way. If you reduce the flux, no volt coil gets demagnetized and will turn off the entire motor. Okay, that's what one of the disadvantages. Then we'll go for 4-point starter. All right. Anyways, this is the answer for this question. Look at this. Look at this. This is amazing. This is somewhere related to the first question what I discussed. Consider the following statements. A DC shunt motor starter ensures that. So which of the following things DC shunt motor starter is ensuring? Armature current is under limit during starting. Absolutely yes. Field flux is maintained at the maximum value. Absolutely yes. Because when you're using the starter resistance, the starter resistance is only connected to the armature circuit, not to the field circuit. Okay, so this starter will ensure field flux is maintained at its maximum value. All right, and acceleration time is controlled because you're moving this. Yes, you will have it. The starter handle. Yes, acceleration time is controlled and the field failure is prevented. It will ensure that field is always in touch. Okay. Next, starting torque is always more than the load torque. Yes, that is why, that is how the good starter design should be. If starting torque is less than the load torque, motor will not start, motor will not accelerate, motor will stop. Okay, so you should ensure always starting torque is greater than low torque, hence the motor acceleration happens. Okay, so all of these statements are absolutely right, so answer A is correct. I think we got a clarity on this. Let's go to the next question. Yeah, this is also one of the popular questions. Just try answering this. Just take a second, it's easy to answer. It's easy to answer. This is one of the popular questions. It asked in once gate exam also. All right. Okay, let me answer this. Which of the following figures given here best represents the variation in armature current and speed during the starting of DC shunt motor? During the starting of DC shunt motor, current and speed are drawn. We have shown this in our course also. During grading of starters, I explained all of these curves as well. Okay, so at the beginning you will have some current and slowly current will reduce as speed is increasing. Then you will change the starter handle so that it will go back again. It will go like this. So this is the starting current and the speed will accelerate like this. So the perfect answer for this is option C. Option C is the perfect answer for this. Okay. So to answer these questions just by looking at it, you have to know the concepts. Now some questions may not be directly given in the concepts or maybe lectures, but the understanding of the lectures will help you to answer the questions, some questions. I'll show you some of the questions also. Let's take this question. This question is not directly taught in the course, but if you follow the course, you will be able to answer these questions. If you follow the concepts behind the course, you'll be able to answer this question very easily. See how nicely the question is built. Very conceptual, very good conceptual questions. That's why I love these Bhimbra questions. Okay. Yeah, try it out. You tried? What is the answer you got? Really interesting, right? A DC shunt motor is started at no load. Its rated speed is noted as 1000 RPM. So you have a DC shunt motor, started at no load. Rated speed is 1000 RPM during winter season. Winter season just started, no load, rated 1000 RPM. Good. One statement is over. The next statement says, after 5 hours of continuous no load running, it is running still no load for 5 hours. 5 hours it is continuously running. Its speed would be, what will happen to its speed? Now there is no change in load. After 5 hours, what will happen? What do you think what will happen? The only thing what happens after 5 hours is, yes, tell me, give it in the comment quickly. The only thing what happens after 5 hours is increase in heat. During winter season, it's already cold start. Now it is continuously running for 5 hours to heat it up. Means the winding, whatever you have, the winding, the shunt field winding, whatever you have, at the beginning, it has some resistance, that is a cold winding resistance, because in winter season it is cold, it's a normal temperature. So cold winding resistance at the starting, once it is run for 5 hours, it has gained some heat, obviously, heat production. So with that, this shunt field resistance is no more equal to cold resistance, it's a hot resistance. Resistance with respect to temperature, resistance increases because it has a positive temperature coefficient. It's a copper winding, okay, which is positive temperature coefficient, right? So resistance increases after 5 hours for the field winding. Once the resistance increases, field current reduces slight reduction. Yes, slight reduction. Now once this current reduced, flux reduces slightly, shunt field flux reduces slightly. If shunt field flux reduces slightly, then speed increases slightly, because we know speed is inversely proportional to flux. Slight decrease in the speed will slightly increase the speed. Okay. That's what the property of this. Even the ferromagnetic material properties also, those magnetic materials also, the magnetic property I'm talking about, with the increase in the heat, its magnetic properties are reduced. Okay, so that way also there is a slight reduction in the flux. Ferromagnetic material property I'm talking about, that way also speed will slightly increase. So whatever it is, after 5 hours of continuous running on the same no load condition, becomes somewhat more than 1000 RPM. Is this a good question? Just give it a thumbs up if you like this question. If you like the concept, give a thumbs up to this PS Bhimbra, man. Amazing, amazing questions framed. Okay, let's go to the next question. Give it a thumbs up, come on. In DC machines, yeah, I think it's easy on you to answer this question. Yeah, this is a very easy question. Try answering this. Very easy. In DC machines, constant loss is composed of. So in DC machines, constant losses. What are the parts combined? We'll call it as a constant loss. Obviously, the rotational losses, because as long as speed is constant, rotational losses are constant. Rotational losses plus iron losses plus field current losses, shunt field losses are combinedly all called as constant losses. Now you may say, sir, it's a DC machine. How come iron losses, which are eddy current and hysteresis losses, are present in iron losses? I want you to answer in the comment. In case of a DC machine, how come iron losses are present? Yeah, I want you to answer. This is a beautiful part. So this combined we'll call it as constant losses. Rotational losses means friction, windage, and iron loss. Combined we'll call it as rotational losses. Okay, these three are called rotational losses. Okay, rotational loss plus field circuit losses, we'll call it as constant loss. All right, let's go to the next question. The efficiency of DC shunt motor is maximum. I think this is also easy. Maximum efficiency condition. Yeah. Armature ohmic loss is equal to the constant losses. I think armature circuit loss is equal to the sum of no load rotational losses and field circuit losses. Yes, answer D is correct. Option D is correct. All right, this is a simple one. Okay, let's see another question. Good. Wow. Try it out. Try it out. This is really good. Try this. Amazing one. Amazing one. I think you may get trapped also. Let's see how many of you handle this question nicely. Done. Okay, let me answer this. I think you must have tried something. So let's try to answer this question in a smarter way. Okay, this is a numerical type question. In a DC generator, first understand the question carefully, what he's trying to ask. And I gave all these key slight differences, very slight differences, all these details I have given on the course. Okay, if you follow the course, it will be very easy on you to answer this kind of questions. Okay, and the courses are of very less price, believe me. If you want for free course, for free lectures, for free if you want some courses, no sir, I can't even pay this 599 rupees also, then you just contact us on WhatsApp. Our team will help you to provide some of the free courses available on the web. They will give it to you so that you can follow those courses. Whatever it is, come on, yeah, it's just a cost of a biryani. Okay, just a cost of one biryani, what you have at one session. So 1 month course you will get. It will change the way you perceive the engineering for sure. Just watch our trial videos, free videos. There itself you'll understand. Anyways, come back to this. I explained, what I'm trying to say is I explained all these concepts there. Okay. Yeah. A DC generator has an efficiency of 90%. Okay. Efficiency of a generator is how much? 90% for an output voltage and a current of this much. For a DC generator, efficiency formula is, can you tell me what is efficiency formula? Do not say output by input. You should say output by output plus losses is a perfect way of writing efficiency of a generator. If someone asks what is the efficiency of a DC motor, then you should say efficiency of motor is, yes, very good, output, sorry, not output, input minus losses. Input minus losses. Technically they are same. Input minus losses by input should be your answer. Technically they are same, but conceptually there is a difference. Conceptually there is a difference. I explained all these differences in the course. Anyways, coming back, output is given as 250 into 18, a product of these two. Okay, so output is equal to 250 into 18 is 250 into 20 is 5000 minus 500, 4500. 4500 watts is this product. Okay, if the machine is made to operate at the same speed as a DC motor with the input voltage, means speed is same, means losses are same. Means losses are same. Okay, as a DC motor with the input voltage of, okay, if it is a generator, output is this. If it is a DC motor, input is this. Input is this. Means what it's trying to say is, this is 4500 by 4500 plus losses. The efficiency is given as 90%, means this is equal to 0.9. This is equal to 0.9. This is what given in the first go. And the second, what is asked is efficiency of motor when input is this much. Input is this much means 4500 minus losses is, we'll have to find out the losses from this. From this equation, the only unknown thing is losses. The only unknown thing is losses. Okay. If you find out the losses, take it to the other side, 4500 plus losses. So losses you will get it as, so 4500.9 is 5000. If it goes to the other side, it is 500. Yeah, 500 watt is the losses from this equation. Simply I did 4500 by 0.9, which is 5000. Okay, and losses comes to the other, losses is here, 4500 is the other side, 5000 minus 4500 is 500 watts. So losses is 500. So here losses is 500 because it is running at the same speed, same currents, so almost same losses. Almost same losses. So the efficiency now will be 4000 by 4500 is a motor efficiency. So far we didn't use much of calculator. Now if you calculate this, you will get something close to, yeah, not something close to, exactly option C, 88.88%. Don't just consider, sir, everything is same, power is same, all are same, so efficiency also same. No, it is not, because in case of a generator it is output, in case of a motor it is an input. Okay, be careful with that. Yeah, I think this is clear. Any doubt here? Any doubt? Is this clear? Fasak. Okay, let's go to the next question. Try this. Not that difficult. These are all PS Bhimbra questions. Beautifully framed questions. Exams are coming up. Guys, get ready. Get ready for Transco or whatever the exam. GATE is coming. Yes, this will be helpful. These concepts will be helpful. Okay, let me answer. Somebody has answered already. Rajesh is having some doubt, it seems. Guys, you ask your question, Rajesh. Some of you, if you know the answer, try to answer that. We are now going ahead with this question. A 200 volt DC shunt motor delivers an output of 17 kilowatt with an input of 20 kilowatt. Okay, you have a DC shunt motor, and the field winding is, okay, quickly, this is field winding of 50 ohms and armature resistance of 0.04 ohms. Okay, let's take the losses are clearly given. Delivers an output is this one, means full load losses. Full load losses is equal to 20 minus 17 kilo, which is 3 kilo, which is 3000 watts. Okay, and what else? Yeah, that's it. So in this 3000 watts, what is the armature, what is the armature current? Tell me. Yes, that's good. What is the shunt field current? Shunt field current is, you are giving 200 volts here. So shunt field current is 4 amperes. 200 by 50 ohms, which is 4 amperes. Okay. Now, what is the total input current? Because it is said input power is 20 kilowatts. Input voltage is 200 watts, 200 volts. So 20 kilo by 200 is the input current, which is 100 ampere, Now this current is 96 amperes. Okay. Now let's try to find out what is the armature copper losses, I square RA. I'm trying to find out what is I square RA. Okay. See, for me, it doesn't really matter if you take 96 or 100, because resistance is very small. 100, we're multiplying with squaring with 100 square, 96 square, almost is going to be the same. For approximate calculations, it will be easy on me to take 100 square rather than take 96. Means I'm trying to say, you should actually take 96 square into 0.04. But for the approximate calculations, what I'm doing is, I'm doing 100 square into 0.04. Okay. For this, you will get something close to, because the options are, much distant, not so close. So I can take this flexibility, I can take this relaxation. So we'll get the final answer as 400 watts. 400 watts is the final answer. Okay. So actually speaking, it will be something less than 400 watts. Because I don't have a calculator access. If you have a calculator access, you can directly do this. Okay, if you have calculator access. If you don't have a calculator access, take some liberty of doing the approximations. Okay, for the easy and quick analysis, so that you can easily answer the questions. So 400 watts, but actually speaking, it will be less than 400 watts. Whatever. Okay, these are copper losses which are incurred during the full load. Then what are the constant losses? Total losses are 3000. Out of this, 400 you remove it. So constant losses are equal to 2600 plus watts. Okay. Plus means, because it is minus, so it is with plus. Okay. Now it is asked for maximum efficiency will be obtained. When the maximum efficiency, just now we have seen the condition in the previous questions. When constant loss is equal to the, when the ohmic loss is equal to the constant loss, maximum efficiency will occur. Okay. So then the ohmic losses should be equal to 2600 plus. Means which the option is matching. Yes, exactly. This option is matching. 2600 plus close to. So you will get this. So means exactly if you try to solve this, you should be getting this one as 368 watts. If you get this as 368 watts, this you will get it as 2632 watts. So that's what exactly this number. If you have a calculator access, you can just verify with that. All right. And somebody has answered also as B, but B is wrong. Dragon Marvel. It is actually A is correct. Okay. It is not asked for full load losses. It is asked for maximum efficiency. Under maximum efficiency, what is the armature ohmic losses? Under maximum efficiency, armature ohmic losses equal to the constant losses. I hope you got the point here, guys. Let's move to the next question. Wow. This is really good. Try it out. Try it out. Let's see how many of you are going to answer this. The easy one, conceptual one, amazing one too. Okay, try this. Try to match whatever you know first. Then according to the options, you can figure out the other things. So first the question is asked for large DC series motor. In case of large DC series motors, you will have a series field winding. Okay. And you will have compensating winding to compensate the armature reaction, and also you will have interpole winding. Interpoles also present. This is a concept. Okay. Accordingly, let's see. Look at the questions first. In case of large series motor, we know we have these. We'll have these. So in all of these windings, what is the purpose of series field winding? Yes, series field winding is to generate the working flux, because that's why it is a series field machine. In case of series field machine, the actual working flux is generated by series field winding. So A is mapped to option 3. So these two are ruled out, only these two are there. Okay, so from these two options, you can directly say B is mapped to option 4. B is mapped to option 4. Okay, because according to the options, now you may say, sir, how come shunt field winding is present in series motors? Yes, in series motors you will not have shunt field winding. But in some special cases, careful here, but in some special cases, series field machine is not actually series field machine. It is actually short shunt compound machine. What is that? Short shunt compound machine. Large series generators or motors are connected with the shunt field winding across the armature. Sometimes special cases. Why? Because there is a dangerous problem with the DC series motor. What is the dangerous case? The dangerous case with the DC series motor is when load is not connected, when there is no load connected to the DC series motor, mechanical load. Okay, I'm talking about when there is no mechanical load connected to the DC series motor, it will pick up the speed to infinity. It will come out of the setup. It will pick up the speed, very high speeds. So in order to limit that dangerous case, you should always try to have some flux even when there is no load. So how to do that? That is possible only with the shunt field winding connecting a shunt field winding. That's what we'll call it as a runaway speed. Okay, to avoid runaway speeds at no load, we sometimes use shunt field winding. Anyways, for that, you just keep it aside because there is no conflict of interest here. These two options are having these two 4 common, so leave it. If you want the analysis, this is the analysis what I given. You follow it. But in general, series motors does not have shunt field windings. In special cases, we do have this. All right. Now coming back to this. Compensating winding. Commutating pole means interpoles. Okay. Interpoles are used to avoid sparking. Interpoles are discussed armature reaction. If you watch the free video which is available on YouTube, just search for armature reaction PiSquare video. You will get amazing animated lecture, which is one of our popular videos. Also, we'll link that in the description as well. Just check it out. Phasor diagram videos, Y series questions, amazing Y series questions also there. Just check all those videos. Your concepts, your understanding of engineering will enhance much level, much better. All right. Anyways, so commutating winding or interpole winding is used to avoid the sparking, and compensating winding is to avoid the field distortions. Because of the armature reaction, there is a demagnetizing effect as well, cross-magnetizing effect as well. To handle the cross-magnetizing effect, we'll go with compensating winding. And for large machines, yes, we use compensating winding as well. I hope you got these concepts clear. And this is one of the popular things which is also armature reaction concept and commutation concept. This pair of concepts, armature reaction and commutation, is very important for DC machines, because that's what armature reaction and commutation combinedly is making DC machine is happening. That's what main beauty lies over there. We try to understand that. We have free videos on that in our PiSquare YouTube channel as well. Okay, so let's go to the next question. I think we're done. Okay, that's the end of this question. I come up with the 10 questions in this part 12. In the next session, I'll come with the next 10 questions as well. Okay, so we'll try to complete these DC machines in a couple of days. It just was a complete series right from the beginning if you have not watched already. And if you want more, understanding of the concepts with the beautiful animations, you can always check our website or download the app. Try to watch the free videos. You're gonna love these animated videos. Okay, as a PiSquare name says, what does the PiSquare tagline says? We help in bridging the gap with multiplied effort. Our team is trying our best to bridge the gap, what you have and what actually the concept is, with the beautiful animations. The multiplied effort means, yes, we're putting our all efforts to design the animations to make the concepts seems very easy for you. For you to better understand the concepts. We're trying our best. That's the end of this session. Happy learning. Enjoy the learning in PiSquare style. Have a good time. Bye-bye.